boiler components in thermal power plants nationwide, utilizing NDT techniques. Continued the research journey as a scientist at the Central Manufacturing Technology Institute under the Ministry of Heavy Industries. During this time, developed a solid foundation in research and development, actively collaborating with the multidisciplinary teams to design, develop, and optimize products tailored for diverse industrial and scientific applications. Leveraging a strong background in advanced material science and technology played a key role in driving innovations and improving manufacturing process. This experience involved working on cutting edge projects using in depth knowledge of micro and nanotechnology to address complex challenges in product design, material performance, and process efficiency for various sectors. Currently, he serves as a head of application specialist India and SAARC countries for Carl Zeiss, Germany, a leading global company in advanced microscopy solutions. With over 17 years of experience in electron ion microscopy, has made significant contributions to the fields of micro and nano product development and material characterization. Leads a team of specialists providing a technical support on material characterization across India and SAARC countries, known for leadership, mentorship, and training junior scientists with a proven ability to solve complex problems by collaborating with both internal teams and external partners. Sir, it is a great privilege to have you as a resource person for this national workshop. Sir, welcome you for this workshop. Now the session is yours. Sir, please.
Yeah. So thank you so much for such a detailed description of my profile. But having said that, though it looks exhaustive, but it's still a learning experience for me when it comes to material characterization. Every day is a new learning for me with new components, new products, new materials or alternate materials. So thank you so much for inviting me to this workshop, and I extend my gratitude to the inviting conveners and the faculty members from Department of SRMTRY. So it's really honor to be here. So I think it's one of the most challenging session post lunch discussion. Technical discussion is always a little tricky. Let me try to keep it as interesting as possible so that we are active in this. So it is not a typical lecture. I just wanted to share my experience, what is happening when the recent trends of microscopy research or material characterization. So that's the experience sharing I wish to have with the faculty members here. And please do not hesitate to stop me if at all there is any question, or you can always post your questions in the chat box, and post the presentation. I can also take the questions and try my level best to answer them as well. Yeah. So with this brief introduction, the topic that I wish to discuss today is it's pretty simple when it comes to material characterization, because we all understand what is characterization, right? It could be any material. We wanted to understand its structure, understand its behavior, and its properties as well. Because end of the day, we choose relevant materials for the identified application so that we are getting the best yield and durability of these materials taken for whatever may be the applications, right? So that is what we do. But what is happening in the recent past? What is the mega trend? How this particular technology of microscopy is taking over the other techniques when it comes to a holistic understanding of materials characterization? Yeah, because if we get into the details of characterization, we come across, if you try to categorize, it's either microscopy technique or spectroscopy technique, right? Most of the characterization techniques that comes in micro or nano, or for that matter even atomic scale measurements, it falls in either one of this category, right? And yes, I spent good number of years on innovation that is happening in the world of microscopy and how it is, that's why I choose the word revolutionizing, meaning this is the most quick paced evolving industry where the requirement or the demand for material characterization is going, it's kind of growing exponentially. So that's the experience I wanted to share, and what Zeiss has contributed and how Zeiss has innovated these technologies to meet the market or the scientific requirement in the field. That is what is the plan I have today. So, a quick agenda is I wanted to give you an insight of what is happening in this space of material characterization, both academia as well as the industry, and then quickly introduce a unique workflow where we are trying to bridge the gap between different length scales. As we keep moving, you will have far more better understanding on it. And then I have some of the applications where this technology and this complete holistic workflows has contributed a lot. For example, some of the key topics like as you see here, it could be energy materials, starting with the batteries or engineering materials like metals and metallurgy, or raw material industry like geoscience, nanoparticles, and even this is not limiting only for materials and raw materials. It is also getting expanded to life science applications as well. So this is the quick, agenda that I have today. We can go in detail, take a deep dive into each of this topic, but let me try to keep it in the surface level because my idea is to create an awareness of what is happening in this space, and maybe depending upon the questions and depending upon the interest, we can further take a deep dive. Yeah. Now, what is happening in the the characterization at present? Yeah. The major challenge, as I did mention some time back, is how are we going to bridge the gap? What do I mean by bridging the gap? We start talking about characterization in atomic scale or nanometer scale, or even to a larger extent, micron scale. But what is happening in the macron scale? Yeah, let's take a turbine blade or the engine wing of any aerospace. It could be a commercial flight or a fighter jet. Typically these wings or these blades or it goes to half a meter or 1 meter, but the material that is actually investigated to understand the property, we are trying to see it in nanometer or atomic scale level. So what we understand in the atomic scale level, can I extrapolate to the complete 1 meter? It's always very, very subjective, right? Because the entire manufacturing scenario has moved from top down approach, meaning from bulk to nano is gone. The machining process is gone. We are now trying to do it as a building block. So it is always, bottom up approach. So when we wanted to understand it in the sub nanometer or atomic scale, how well we are able to extrapolate for millimeter scale or centimeter, or it could be even meter scale, the macro scale. That is where the actual challenge comes in. So that's why it is called as a multi-scale problem. Yeah, how we are going to bridge this. Now, what is happening in the world of microscopy is we all are aware of the transmission electron microscope. Most of you would have come across, or most of you would have used in as part of your research in the past as well. And we also use the scanning electron microscope. Yeah, so these two technologies are well established, well adapted. It's really hard to come across any research center or central instrumentation facility which does not have a TEM or an FESM or an SEM, right? So it is a well established technique, but the major challenge is yes, we have answers or characterization technologies for submicron to nanometer, subnanometer scale. But what is happening in micron scale? What is happening in macro scale? We do not have an understanding of it. That's exactly where the next set of technology development started happening. It is called as the focused ion beam machining, where we start talking about in the tens and hundreds of micron scale. Then we also talk about non-destructive technologies like X-ray microscope, which has capabilities of going down to, or going for sample size in centimeter level. And when I say centimeter level, we are talking about tens of centimeter. So that's exactly is the approach, and we are no more talking about only two-dimensional characterization, because whenever you do a TEM or an SEM, we are talking about surface information or two-dimensional information. But now we are slowly moving. The scientific requirement is moving towards three-dimensional and also the fourth dimensional characterization as well. And when I say fourth dimensional characterization, it is the functional characterization, how a material starts behaving when it is subjected to various conditions like high temperature, pressure, or tensile loads, whatever it is. So how it starts behaving. So that's the fourth dimension as well. So there is a shift in this, and what we are trying to do in Zeiss is we introduce some of the niche application, and I mean niche technology for cutting edge applications, where we are talking about non-destructive testing, and how from a macro level you can slowly reach down to the atomic scale, where you can correlate, meaning there is a complete flow of characterization data as well as understanding of the material, all the way from macro scale to micro to nanometer as well. So this is the complete workflow that we have established, and it is really creating, it's kind of a disrupting technology where it is creating a lot of buzz in the market as well. And you can see the level to which it is happening as a result of bringing this into the market. I think I should, yeah, okay. So maybe I will go here first. So you can see what exactly happening in this correlative microscopy. And when I say correlative, when we combine all these technologies together, addressing from macro to sub-nanometer workflows, that's what is called as the correlative microscopy. And now that is the mega trend. Just for an understanding, you can see here, till early 2000s, the number of publication that used to come in this particular space, and when we say publication, we try to take the high impact journals, not the all the other one, high impact journals, and you can see from where we have collected this data as well. So it was hardly 200 publications like 20 years back. Right now, within 20 years, you can see here the growth at which this particular technology has taken forward. It's more than 1700 percentage of what it has happened. Every year it is going at it is growing at 15%. So this has become a major topic of discussion, and the most interesting topic of material characterization, where people started publishing a lot. And it is also with respect to the high impact journals as well, because it is more confirmation on the material's property, not just in length scales, it is across the length scales. And it is also it's not only two-dimensional, we are talking about three-dimensional as well. And this is kind of the split of the sectors where it is getting, I mean, where we observe more number of publication. And you can see here almost all the research that is happening, starting with energy materials, biomaterials, composites, metals and steel, anything, polymers, ceramics, environmental sciences, textiles, fabrics, lots and lots of application that is happening here. And we see significant traction in India as well, because at this point of time we have 10 different academic institutes and research laboratories having these sort of technologies, where they're trying to push the limit of characterization. Now, what is the challenges when we talk about multi-scale? Yeah, it is the major challenges when you move from when you have a sample of a big dimension, where exactly to understand or narrow down to a region where there are some defect. Let's imagine this big block is my sample. How do I know at which particular region there are some defects, or from which particular region I have to collect a sample, so that that gives me the exact understanding of the entire component. So that's where it starts. So in a macro scale, identifying the region of interest is the first challenge. The second challenge is, let's say I identify the region of interest. How am I going to approach that region of interest? And when I approach, without disturbing the structure or the property of that identified region, that is the next challenge. How am I going to access the region of interest without disturbing it? Very precisely, without disturbing it. This is how I mean, that's the next challenge. The other one is, once I have the access to that region, so in this bulk, I have access to this. Next is, now I'm able to see the region of interest. How am I going to prepare a sample out of it, so that from the big bulk scale or the macro scale, I can take it to a SEM or a TEM or whatever may be the next technology for nanoscale or atomic scale of analysis. So how am I going to prepare the sample? That's the third challenge. Last but not the least, after preparation, it should also be prepared in such a way that I get all the analytical data, so that my characterization results carry the vital information on the sample or the component that has been taken for testing. So These are all the four major challenges when we try to address the or bridge the gap between macro to micro to nano, and at the same time retaining the region of interest for the correlative workflow. To identify, then to access, prepare the sample, and then take it for the analysis. So that's exactly what is the requirement. I mean, just to give you a few examples, let's say, let's take battery research. Let's say I have an anode or a cathode, any electrode for that matter. Within the electrode, where do I need to collect a sample, or what is the region of interest where I need to prepare the sample for my analysis? So that's exactly what we have done here. In a X-ray microscope, the data has been captured for the entire electrode. Within the electrode, once the region has been identified, using some of the next technology of material removal using the ion beams or the laser beams, we expose the region. So these are all material that is removed from the electrode, and we prepare the samples. And you can see here these samples are further taken up for the atomic scale or nanometer level of characterization, which could be inclusive of the analytics to try and understand the chemistry or elemental composition as well. We do it for battery research, catalytic nanoparticles, metals and alloys. I do have separate slides on each of these topics to for you to have a better understanding. So fundamentally what we need to do, or the market demand or the requirement is, yes, I wanted to see in the atomic scale or nanometer scale not only how they look like, but what is the constituent or the elemental present. But where do I start? Where do I identify, how I access, prepare, and then I start analyzing? That's exactly what we did with the solution that is called as sample in volume analysis. Meaning within your volume of sample, how volume of your component or a sample, how you can further take samples out of it, which is of you know narrowed down to the region of interest, and without changing or deforming or causing any damage to the sample, how it is taken for the next level of understanding. Let me play a small video for you which gives you an overall understanding, and I hope I enabled my audio. If the audio is not there, please do let me know. I will just stop it and then we can play. Yeah, I hope the you're able to hear the audio. Or yeah, so we identify, access, prepare it, and then take it for the analysis. And that's how is the workflow which is achieved by two different technologies. One is the X-ray microscope, and the other one is the focused ion beam machine along with the laser attachment as well. This is the complete workflow which I'll be explaining in the subsequent slides with some of the examples as well. Yeah. All right. So a quick summary, what we are trying to do is we are trying to identify, that's using the X-ray microscope. Yeah. So that's what we do, starting with identifying using the X-ray microscope, and then accessing the area or the region of interest that has been identified, and then we prepare the samples. Like, it could be a lamella preparation for TEM analysis, or thin probes for atom probe tomography, or we can also start preparing samples for doing uh, this sort of micro pillars for tensile testing using indenters, or it could be prepared for EBSD or crystallographic data collection using the electron backscatter diffraction patterning as well, or it could be simple chemical composition as well. So this is exactly how the workflow happens, with identifying and using the X-ray microscope, accessing the area with combination of both laser as well as ion beam. It's not only accessing, it is also used for preparing it. It could be for TEM lamella or atom probe tomography needle structures, or it could be also, as per the ASTM standards, you can prepare samples for mechanical characterization as well, which is then taken for the analytics like TEM analysis, crystallographic data collection, or mechanical characterization as well. So this is exactly what we do here. Yeah. So this is the technology. The X-ray microscope, it's completely non-destructive technology where X-rays are used for complete data capturing and three-dimensional data capturing, using objective-based detectors, where we are talking about resolution all the way down to 500 nanometers. That's the resolution that we will be able to hit using X-ray microscope, which is used for the complete understanding of the component or the sample in the three-dimensional space, and then you can pick and choose the region of interest. Once the region of interest is selected, it could be one or multiple within the sample. The sample is moved from X-ray microscope to a focused ion beam integrated electron microscope, where we also have the attachment of laser beam as well. So laser beam is used for removing bulk material, so that whichever region that has been identified using the non-destructive technique, now we remove the material and expose that region using the laser, and then you can use the ion beam to prepare the samples. It could be for lamella, nanopillars, cantilevers, or it could be for EBSD analysis as well. Once it is accessed and prepared, then we take it for the analysis. It could be chemical composition, crystallographic data capturing, or diffraction patterns using TEM. It could be anything. Yeah. So this complete workflow is controlled by tested and proven software platforms, which ensures that when you move the sample from one technique to the other technique, it is having a complete coordination between this movement of sample with respect to the region of interest that has been identified, and you do not compromise on the data that you collect from the actual region of interest. So that's what we do. So explaining, or putting it in a workflow. So we took an example of a battery pouch. Yeah, pouch cell. I think you understand what is a pouch cell is. A battery pouch cell was imaged in a three-dimensional non-destructive testing. Region of interest was identified. Then once it is identified, it was dismantled, because it was the whole battery was imaged and data was collected. Then liquid, the electrolyte was drained, and it was taken inside the laser chamber, and all the electrolytes, all the contamination has removed, and the region that has been identified, the XYZ coordinates, also gets transferred from the X-ray microscope to the laser chamber. The coordinates, it goes to the exact location where it has been identified. Then it starts removing the material using the laser ablation. So that's how we access. Once the region of interest is exposed, then it moves inside the ion column or the fifth chamber, and then we use the gallium ion for preparing and polishing, and then it is taken for all these analytics like EDS, WDS, EBSD, TOF sims, or it can be used for TEM and ATP analysis as well. So this is a quick workflow, how it works. If it is battery, I do have examples of other applications as well, which will give you a better understanding, or more idea on how this has been deployed in versatile application areas as well. Yeah, that's what is my next course. I have few application slides, like starting with materials research for energy materials, how it is getting applied in electronics, semicon, industrial research, life science, additive manufacturing, and for some of the examples. I think you would have come across this lunar space mission, where China got some extraterrestrial samples from moon, and they wanted to do understand the chemistry and the properties of those material as well. So we did extend our support to establish that sort of workflows as well. So this is something what I've already shared some time back. So usually we take the electrodes in the battery industry. Once it is manufactured, once it is packed, they do a complete analysis. They identify certain regions of interest. It could be a failure, or it could be a deformation from the actual fabrication or the manufacturing process using the X-ray microscope. Then once it is identified, they use the laser beam for removing the material and exposing the region of interest. Then fifth column is used for the ion beam is used for preparing the samples, and then they wanted to understand the analytics of it. Here it's very simple. The battery started swelling. I think that you would have come across. I mean, people who have used the earlier generation of mobile phone. The challenge with the detachable batteries, they always swell because of periodic charge to discharge cycle. They wanted to understand what is the reason behind it. Actually, the swelling happens around the silicon, which is taken as one of the raw material for the electrodes. And you can see here the cracking and expansion of this silicon particles is where what is actually causing the swelling of batteries. So this helps them to understand how to have a control over these sort of materials and try and see how best they are able to reduce this and extend the lifetime of the batteries. So that's what they did here. And this is automotive industry, and I think you would have heard of this catalytic converters. I think yeah, most of the Indian cars or Indian manufactured cars also post Bharat Stage 6 compliance. Catalytic converters have become an important integral part of the exhaust system of automobiles. So I think we all understand, right? One of the preferred catalytic material is either platinum or palladium nanoparticles. Yeah. So the thought here is, so this is the catalytic converter. So the exhaust, the carbonaceous smoke that comes through, from the engine passes through this catalytic converter, and the effectiveness of purification heavily depends on the channel and the porosity of these structures, and all the catalytic particles, like catalytic materials like palladium or platinum is predominantly present in this porous region. The interest here is to see, after a certain duration of using this catalytic conductor, what is the impact it has created, or how the depletion of these catalytic material has happened. So you can see here they used X-ray microscope to identify the region. And you can see here, right, this is actually a coating, a catalytic coating that is in a particular fashion on the catalytic converter. And in a non-destructive way, when you collect the XRM data, already we are able to see some cracks, right? So these are all complete non-destructive testing where we are trying to see in millimeter scale. And then further, it was taken for sample preparation from there to be put under TEM. So you can see here the sample has been prepared and it is put under the TEM. They wanted to understand the distribution and the locations of the cerium and zirconia rich area, because those areas is where predominantly they try to withhold the catalytic material. So that's exactly what they did. And it is it's low dense material, and they actually wanted to do with the yields as well, the energy electron loss spectroscopy, to understand the remnant of the catalytic particle. This is a huge topic of discussion because the catalytic material is quite expensive, and its availability is also scarce. Palladium and platinum, right? So it's very, very expensive, and for an automobile and a catalytic converter, it's not affordable to spend a lot on these sort of catalytic converters. A quick example for life science. This is the mouse retina damage. Yeah, the retina, as you can see here in the eyeball at the edges, you have the retina, which is damaged, and they wanted to take they want to narrow down, capture the complete retina, and then see where exactly this failure has happened, or the deformation, the damage has happened. And you can see here they did the non-destructive testing. They identify the region of interest, then they did the fixation and staining. I think this is something people from the life science or biological science will have a better understanding, because when you do microscopy analysis on life science samples using electron microscope, you always need to do heavy metal staining, or else the contrast difference will not show you the difference or differentiate different organelles that is present in the life science samples, right? So that's exactly what they have done, and they have tried to see how precisely we can cut and take a small, a pillar like 200, 400, and 800 micron tall sample that was further taken for the next set of analysis to try and understand how the damages happen, because they wants to understand the nerves and all the other organelles present in the retina as well. So there is no limitation of applying these technologies to life science as well. And the next example is additive manufacturing, one of the hot topics even in India as well. So here you can see here, this is a gear component which is manufactured through 3D printing, yeah, metal 3D printing, additive manufacture. But there are lots and lots of challenges when you go for additive manufacturing, starting with the dimensional accuracy, because there is always a shrinkage factor comes into picture when you do the additive manufacturing, and when you try to anneal the sample for improving its tensile property. So starting with the dimensional accuracies to the internal unsintered particles, contaminations, foreign particles, voids, cracks. So lots and lots of challenges are there when you do a additive manufacturing through 3D printing. So this complete workflow helps them to understand or enable them to inspect the complete component and very precisely understand where there are unsintered particles, because it is a laser sintering, right? Where there are unsintered particles or satellite particles, where you observe some voids or cracks. All this can be done, and here in this particular example, what they found is they found contaminations in the sample that was manufactured through additive manufacturing. So you can see here it had iron and chrome in a, I think this was an aluminum. Yeah, this is a, yeah, aluminum or titanium. I think it was a titanium gear, and they found uh, contaminations of iron and chromium in one particular region, which was identified non-destructively, and then it was taken down until we were able to have the complete analytical information. And this is what we do in the additive manufacturing as well. So that's what. And this is an example for samples that was collected from the lunar mission from Changi. I mean, Changi is uh, the space mission for lunar expedition, and they brought in some of the samples, and you can imagine the importance of these samples, right? Because these are all samples which are not easily accessible. They are like golden samples. So the interest was to identify regions or identify whether these materials had any metal presence. Yeah, so they were able to identify presence of zirconia in the lunar soil sample. So how did they do? They took few granules of the soil that was collected from the space, the moon, the moon surface. They brought it. They did the complete non-destructive testing. When you do a non-destructive testing using X-ray microscope, nothing is going to happen with respect to the sample. It is preserved forever. Yeah. So during the screening process, as I said, their target was to identify the presence of zirconia. So wherever they were able to see a huge contrast difference, because X-ray microscope always gives a contrast difference between high dense to low dense material, or the contrast difference depends on the atomic number of every material present in the sample. So they were able to identify some of the bright region where it could be, the possibilities of metal was there. So once they identified those granules, they took it for laser followed with ion beam for exposing that region, and then that region was further subjected to chemical composition analysis, and they were able to identify that zirconia was present in the soil samples that was collected from the moon. The message here is, instead of doing a blind testing without having a good understanding of where do I expect to identify the presence of this mineral. Now this has become very, very easy and convenient, because with this technology you have the you have the comfort of doing the entire screening process and then going to the next level of the analyticals as well. Same thing we did it for semicon display samples. Yeah, display is very, very crucial for starting with your smartphones to the laptop screens, and you can see the pixel densities to the resolutions to the high dense colors. Everything is becoming even more and more important, from LCD to LED to whatnot. Yeah, you see lots and lots of innovation happening in this space. At the same time, the durability also has increased, right? Previously, let's imagine, like 10 years back, any of the smartphone, if you would have dropped in the floor by mistake, the first thing that gets damaged is the screen, right? Now people are saying that you drop it, it has been drop test has been conducted, and even if you drop a handful of times, the screen is not going to get damaged. Now, how did it all happen? It is all because of the improved quality of these screens without compromising on the performance of the screen as well, because the touch resistance is very, very important. So now here the interest is to try and understand how the defects are getting originated when you want to prepare or when you want to manufacture these displays. Yeah, so you can see here, this is a complete non-destructive data that has been collected from the displays, and they identified a particle at a 6.5 micron diameter. Yeah, that is a particle that they identified. Once it is identified, the region was fixed. The sample was transferred to the next microscope, which is a laser FIBSIM, and the laser was used for material removal. And now you see here, once it is removed and it is polished using the ion column, you're able to see the particle here. Yeah, so they were able to see the particle here, and yeah, you can see here, this is on the OLED, I mean the organic liquid display unit. So they were able to identify this. And oh, there was an analytical data. I'm missing the analytical data. Okay, all right. So anyway, so this is another example for the semicon application as well, and it is not necessarily only on displays, even chips, IC boards, PCB boards. We do this for all these sort of applications as well. So with this, I wish to conclude my session, because I would like to have, take questions from your end. So before I open the floor for questions, I would once again express my gratitude for inviting me here, and as well as thank you so much for the participants' patience to listening to my talk. And I open the floor for questions.
Sir, thank you, sir. Thanks for your enlightening lecture, sir.
Yeah.
So participants, please type your question in the chat box, or you can unmute and you can ask your questions.
Yeah.
There is a question in the chat box, sir.
Okay, I'm just trying to see where is my chat box, because I'm sorry, I very rarely. Okay, here it is. Okay. Okay. Oh, not this. It's here. Okay. Hmm. Where is my chat? I'm sorry.
Otherwise, can I read the question, sir?
Yeah, I think I in call messages. You can pin the message. Yes, sir, please, sir. Okay. I found it. How? Oh shit! I did it back. Oh God. Okay, where is the chat box? Sir, if you don't mind, please go ahead, sir.
Yes, sir. How important doing this way, doing this X-ray and ion beam spectroscopy to the nanomaterial for battery applications, sir?
Oh, it's very important. It's very important. As I was showing you some of the example, one of the most challenge for the battery sample is its performance, which is yield, right? And maybe you would have heard what is happening, especially after the launch of Ola two-wheelers. Many places the battery is getting damaged. There were some fire incidents as well. So the major challenge is it's a battery pack. They wanted to understand, let's say I have done the battery has been used for 100 hour cycle, 200 hours of I mean, when I say cycle, it is charge to discharge, 100, 200, 300. So they do these cycles, and at some point of time its performance drops. Once the performance drops, We want to understand in the entire battery what exactly started causing this drop in the performance. And I want to understand, or the my industry want to understand where it has started. So non-destructive testing on the entire battery pack is very, very crucial, and we have been supporting to most of the battery research or battery manufacturing industries as well. So it's very important, and it is not only in the manufacturing sector, even for academic interest as well. Let's say, for example, I have been working with Indian Institute of Sciences, Dr. Funny. So he works on coin cells, yeah, small coin cells. After a if I don't have the understanding of the entire cell, the coin cell, it is very difficult for me to get into the level or identify the region where the failure has started, right? So, answering your question, it's very, very important to understand the possible regions where the failure have started happening through X-ray microscope. So that's my answer for it, sir. I mean, I hope it answers your question. If not, you can again ask me. I can give you some examples and explain it further.
The same question has a second part, sir.
Okay.
Is it important for the academic researchers to do this analysis? What will be the rough cost for single sample analysis?
Oh, okay. Sir, unfortunately, uh, I don't have the details of sample analysis cost, but maybe I can refer some of the academic institutes where they offer this services, and maybe you can reach out to them. I can share the details. So one of our renowned users of this X-ray microscope, who has experience of working with battery samples as well, is Dr. Professor Asim Tiwari from IIT Bombay. Maybe I can share the details, or maybe I will uh, give my email address. I will put it in the chat box. So if at all anyone is interested, if you want to know any further details on it, please feel free to drop me a mail. I'll be more than happy to get you connected with Professor Asim, and I can take it forward from there. Yeah. So I have, it's possible, but I'm sorry, I do not have the pricing of this. But yeah, Professor Asim will be able to, or I can drop it as well. So his name is Dr. or I'll put it as Professor Asim Tiwari from IIT Mumbai. Oh, it's IIT Bombay, sorry. IIT Bombay. You can just Google. He's one of the very well-known professor from IIT Bombay. So we'll be able to help you out. If you have any challenges, you can always get back to me. I can do that. Yeah.
There is
Okay.
another question, sir.
Yes, sir. Yeah, sir, Shaktipanan, sir. Now my chat box is visible
Oh,
for me,
okay,
so I
okay.
will go ahead. Yeah. So, excellent session for regions of interest for research. Okay. Yeah. Yes, Mr. Dawal. Absolutely, you are right. It's very, very important. And which is better, lithium iron or lithium phosphate as battery material for longer life? Okay. I mean, I may not be the right person to answer this, because it is not just the material alone. Yeah, it is not just the selection of material. It is also equally important with respect to the combination of materials and the stoichiometry ratio of these materials as well. So I may not be able to give you a straightforward answer, but what I also foresee is lithium may not be a long-term future, or the dependency of lithium will drop in the near future. So we feel that solid state and like sodium ion batteries and stuffs like that, which is more cost effective, and materials which are abundantly available. And they're also going for batteries without electrolyte, dry batteries also. That is also another big research that is happening. And yeah, these are all something that comes to my mind right at this point of time. But yeah, the performance heavily depends on not only the selection of materials, it is also the combination and then the stoichiometry of this as well. So that's a very, very subjective question, and I may not be able to give you a very precise answer. Good. So, any more questions, sir, or any more information? Because I can
Still
keep
no
sharing
question.
tons of details.
Thank
Yes, sir.
you.
I'm thinking of using cellulose-based electrolyte in lithium. Have you heard of this work? Cellulose-based. I have seen a company already working on this. So yeah, that's all I can say. It's not that I have heard, I have seen as well. Cellulose based electrolyte. Yes, I have seen it. Yeah, yeah, no problem. Yeah.
Yes, sir. Thank you, sir. Thanks for your enlightened talk, sir. So,
So I just posted my email address in
your
the
email
chat
ID
box.
you are
Yeah.
already posted, sir.
Daniel, sir.
Ah, yes, yes, Mr. Vinayak. Yeah.
Just I asked the question that you have answered, that you have seen it, and do you have any rough idea like what they have been? Are they getting good ionic conductivity?
I cannot share any details on it because most of the industrial research
Khalid
that
already joined
I'm
that. Our
collaborating,
invitation
I
join
have an NDA with them, so I'm so sorry
join
I'll not be
every
able to share inputs on it. But that's already happening, and I would say it is already in the testing phase, though not come to a manufacturing phase. It is already that to not alpha testing. It is in beta testing. Yeah. So yeah, I'm sorry, I will not be able to give you those information, but yeah, I can answer that question. That yes, yeah, I have seen cellulose, not just cellulose. When we start talking about this metal foam based batteries, are also something. It's a hot topic that is also happening. Yeah,
Thank you so much, sir. I will look into it.
yeah, you're welcome.
Yes, sir. Thank you, sir. Thanks for enlightened talk, sir. We have the second talk also, sir.
Great, great. Okay, yeah.
Thank you, sir. English.
Well, thank you so much for having me here, Shaktipan sir. Appreciate all your support and having me here. Thank you so much, and thank you
Thank
all
you, sir.
participants as well. Yeah, thank you.
Thank you so much, sir. Thank you. Thank you.
Yes, sir. English.
Very good afternoon to everyone. I would like to invite our second speaker, Dr. Khalid Mujasam Batoo, received his PhD degree in applied physics from Aligarh Muslim University, India. He is working as a professor at King Abdullah Institute of for Nanotechnology, King Saud University, Riyadh, Saudi Arabia. Since 2010, he is in the recipient of many awards such as Junior Research Fellowship Award, the Speakers Award, Young Faculty Award, Outstanding Scientist in Nanotechnology Award, Distinguished Scientist Award, etc. As a principal investigator, he has completed many international research projects funded by the National Plan for Science and Technology and King Abdul Aziz City for Science and Technology, Kingdom of Saudi Arabia. He has authored more than 335 research journals published in the peer-reviewed journals of international commendation. His Google Scholar citation has crossed over 9,100. His research interests included nanomaterials, nanocomposites, thin films, magnetism, graphene materials, smart textiles, solar cells, and nanomedicine. He is serving as an editorial board member of more than 13 scientific journals. As an invited speaker, he has delivered many talks on nanotechnology and its applications in various countries such as Egypt, UAE, Saudi Arabia, Hong Kong, USA, China, France, Germany, Turkey, Bangladesh, Uzbekistan, Malaysia, Greece, India, and etc. Now I'd like to invite our guest speaker. Now the session is yours, please.
A very good afternoon to all of you. Am I audible?
Audible, sir.
Okay. So, thank you very much, Professor Sakafadi, for giving me this opportunity to interact with the distinguished scholars and academicians from across different countries, as well as especially from India. Uh, as we discussed previously, that I'm going to talk about something specific about electromagnetic shielding, but however, I tried to modify my topic and I made it a little bit general so that it will be more appealing and more uh, attractive in this respect, that how ceramic oxide materials or simply oxide materials can be beneficial to the future challenges and prospects of research related to our various in-hand usages, what we need and demands, what we can suffice through it. So I will not take much time, and I will begin with my talk. I have been working in ceramic oxides, especially the ferrite materials, magnetic oxide materials, and the usage of these materials for high density data storage has been the primary application. Then, as the advancement of the research continued, we tried to use these materials for various applications such as electromagnetic shielding. We try to use it for photocatalysis. We try to use it for uh, wastewater treatment, biomedical applications, and many more. So it is just the oxides we are trying to explore, how these oxide materials can be used for various applications as per the demand, as per the requirement. In the recent announcement, since I'm working in Saudi Arabia, a platform like you have in India, we may call it University Grants Commission. Uh, and according to the University Grants Commission, there are rules and regulations, or the CSIR or DST, you have the call for the projects by the different various government organizations. Similarly, we have been, uh, sum up in a one institute, that's King Abdullah City of Science and Technology. It's likewise as a UGC. You can say it, who is regulating the research activities across the kingdom. So they recently launched one program that's called RDI, Research Development Initiative and Attraction, which is inviting the different scholars, academicians, engineers, scientists across the country for various topics which are challenging, such as energy, health sector, and water. So these are set up as a national priorities. So here in Saudi Arabia, we cannot submit the proposals or the research. We cannot go as just randomly for something like somebody is doing in health research. Cannot go for any sort of topic, any sort of research. Rather, he is being guided that he should look into a particular research topic, such as after the COVID-19, we had one program that how communicable diseases are COVID-19 or SARS-like diseases can be avoided. So there is a challenge for the next 30 years. So how similarly, as the breast cancer is increasing, how this can be reduced. Or in the energy sector, the most of the consumption is happening here with the hydrocarbons being utilized. Almost 10% of the extraction, whatever is coming out, is being used for the energy sector. So the renewable sources of energy are being thought how these can be utilized. And since Saudi Arabia, especially having the largest desert after the Sahara, in South African continent, this desert has the potential to have a lot of sun energy which can be fed to almost 22 Gulf countries. That has been estimated. So in that prospect, the oxide materials are becoming more attractive, how these materials can be utilized for various challenges. So if you go to the recent history of the how these oxide materials have been challenging, these materials have been giving us a lot of fascinating properties. Like if simply we are talking about oxide materials, we have oxides such as we talk iron oxide material or some other oxide materials. These oxide materials give us various properties from different six parameters of magnetism. If we talk like ferrimagnetic, paramagnetic, diamagnetic, superparamagnetic, or ferromagnetic properties. Apart from that, what sort of magnetic or electrical properties they can generate. So first, it was just simply we were examining the oxide material as a particle, then as a compound. Then recently, in the year 2007, this is the paper published in Science Journal, where it was some that if we put the oxide materials over layer, we can have the different properties. These heterojunction materials can give us GMR, TMR, or is similarly now the same heterojunction properties are being examined for photocatalysis, water splitting, hydrogen production. So it's not restricted upon to the limit of one dimension or one layer. It is going to be the heterojunction layers. Just it is just as the exhaust is the material, as the one material is being simply discussed in depth, then the next stage is how we can change the dimensions of the material, how we can tune the properties of the material. So that way, this was a very important paper. And as I mentioned that these oxide materials have given us face-to-face different values, which I discussed, like six different properties of magnetism. Apart from these six different magnetism, they also give us spin canting like properties, multiferroic properties, depending upon their geometry, depend upon their sizes, depend upon their manifestation, how the fabrication has been done. So the oxides are fascinating. If we go a little bit back to our history, let's remind ourselves that how the computer evolved. And it was not first a computer. I am just giving you a brief about how this development has happened with the emergence of the oxide research. So it was basically ENAC, that's electronic numerical integrator and calculator. It was just an electronic calculator which was developed long back in the early 50s. So this computer was installed in, or you can say the system was involved in 7-story building. So where you can see this man, he is in this region. He is just pulling up some wires, and the same is done here by people. The two ladies. Same is done by these people. So what they were doing, it was just an instruction coming from the monitoring room or the calculation room. They were saying that we are going to do this and that. So they were just accordingly, replacing the cables, moving the cables, and or they were using, replacing the tubes, bad tubes, in case there is a malfunction kind of thing. So here is the calculator room, or you can say typically the monitoring room of the IBM 7094, where mostly almost 100 people were on the desk. They were doing the calculations. And next to you can see this was the printer used at that time, and this is the paper which was being used in that printer. The punch, you can see the hole in the paper was representation of the 0, and without no punch means the 1. It was unfortunate or the fortunate one. But for the integrated circuit technology, or you can say the computer technology, it came as a binary function later on. So 0 and 1 were the binary numbers developers. However, in the paper, it was 0 was considered as a punch in the paper, and no punching, the space where there is no punch, it was considered as a 1. So that was the kind of a language being written at that time. However, with the advancement of the ceramic oxides, as we had, the development of the PN junctions, from PN junctions, we went to the IC technology, And with the advancement of IC technology, we got our computer in 7-story building got compacted into a one box, and we got this is the first IBM personal computer, later on by the Apple. And then we had the more developments. Then we got laptops, we got iPads, we got iPhones, and then memory devices got better and better. However, before you see that how this advancement has happened, you can see and relate to yourself that this was when the in 1930s the mechanical counter was used for the, as I mentioned, for punching for the calculation, and this was the 1960s RAM memory, which was built in 1960, early 1960s. It was, the cross sections you can see, the wires you can see, and then in the 1989 with the emergence of IC technology, PN junctions, and here you can see this was the first 1 mega chip, which was developed by Webb Carroll Zeiss technology in 1989. However, you can see now it's in 2020. I have used this picture of 2020. Now you have more than 16 GB RAM available. Now you have the SATA and other things, kind of RAM devices for the installation in the computers. However, one of the important aspects is with the battery technology we have and the RAM technology, what we got, we have two types of memories. We have volatile memories and non-volatile memories. In a random way, if we may say that what is the volatile and non-volatile. I will give you just a simple example of that. If you have a laptop, you are working on a laptop of Dell computer or any other company, HP. So you are working on some Microsoft, or you are working on some web page, and then suddenly the light has gone and power has turned off, your data has gone. So that's called a volatile memory. However, if there is as the addition, one addition, that your light has turned off, but you resumed the work from where you have left, that it's not a volatile, it's a non-volatile. That's being nowadays being worked out, that even though the light may turn on or the data is settled there, work is settled there where we have been working. And in that case, we have different type of volatile and non-volatile memories, and especially in the MacBooks or Air pads, this technology has been embedded by the Apple company, and they are working on it. And even if you have a MacBook, you just your light has gone, your battery has drained out, and you can still resume your work from where you have left after almost 2 hours. So that's the case there. And so non-volatile memories are very important in the memories nowadays. When we see with respect to the growth of the data versus the growth of the data analysis, there is a huge deficiency. That's a huge deficiency. As the population has grown, we are now soon somewhere 8 billion people. So every country has become digital. So the paper less commitment is everywhere. No paper currency, no paper for the files, for the documentation. It is just all getting digital. However, to store that data, there is a huge deficiency. We can say that stored data accumulation at 28% annual growth rate is there, while as data analysis in workforce growth is just 5.7%. So as we are approaching in 2025, and you can see there is a huge gap between the data available and the data storage. So although now with the emergence of the 5G technology and other technology, you can see that there is a big demand, whether it is about the storage, whether it is about the networking, whether it's about the CPU performance. And you can see as with the progress of the years 1970, how the storage has increased, and the cost has increased. And similarly, you can see from 1969 until today, the networking has increased. We are using data cables, and internet has become faster and faster. We are using optical fibers. we are using the plasmonic. Last time I gave the lecture to the community about how the plasmonics can be used about the data transfer, which moves very fast. So that is also something which has really enhanced it, which has gone too high, and it increased it in a better fashion. However, again, we have the issue with the cost. Yes, in certain regions there are cost issue is there, or the manipulation of some companies are there. So the regions like Africa is still struggling with that. Internet is not as cheaper in other parts of the world as it is currently at India. I may say it is much cheaper compared to even Saudi Arabia. However, in Saudi Arabia, it's much faster. The downloading speed, the processing speed is higher compared to other countries, as I personally experienced while being in India and China and other parts of the world. So it's much faster here. So that's the one issue which needs to be sorted out, as it is related with the cost. And similarly, the cost of the it shoots as the storage capacity is required and is in demand. So it is a kind of a future frustration when we are discussing with respect to the Moore's law, that says that with the demand from 1971 to 2008, it is the data, and you can relate it, as I mentioned it, in 2025. There is already a huge gap between the data and the data analysis, and the data storage is itself one aspect where we are struggling. That means we cannot have the more and more joint data storages as a hard disks are the computer systems where we can put every data. No, we need some kind of a device which is portable, which is cheap, which is accessible in every district, in every town and the city, so that we may not rely on the the headquarters where we have the send the data, or the clouds. So we are working on the iClouds. So those need to be cheaper. So in order to being assessed by the common people. So that way, if you look, the more you said that there will be a huge frustration and there is a huge gap, and we may need more the billions and billions of the chips in order to store this kind of information. However, in that case, we may say that nanotechnology is doing its best. It is doing its wonderful. It's doing wonders. That's true. So let me go back to this oxides, as we discussed it somewhere, as I am going to talk about related to these memory devices and other things. What I personally have done, I'm going to present my own work. So in case you are very familiar with the oxide material, you know that broadly they can be divided into 4 classes: insulating, metallic, superconducting, and conducting materials. Apart from that, you have the different, from these prospects, you can think about the different applications of these materials. For example, we are talking about the bandwidth, and we are talking about the RAM devices. They are the semiconducting materials, while you are working on the superconducting materials that can be used for the superconducting quantum devices, quantum computers, and they can be used for other projects as the application is being determined. So again, you can determine these oxide materials as per their transistor metal, what sort of transistor metal it is. So they can be divided into a magnetic class, if I may say. In the magnetic class, they can be divided into ferroelectric, ferromagnetic, superconductive, dilute magnetic, semiconducting materials, colossal magnetoresistance, and superconducting materials. So these 6 types of properties of magnetic material, they determine their own characteristic applications. Ferromagnetism, in such as in memory storage, supermagnetism, as I mentioned, in the quantum computer nowadays, are you have the fastest rail projects in the Japan. They are working on the superconducting materials, and dilute magnetism. You have zinc oxide type materials, and they are having the lot of applications and lot of usages, as you are very well aware about that. And super paramagnetic materials nowadays being used for in ferrites, one of the class of the property is supermagnetism. Again, it has its application in biomedical, and similarly colossal magnetism, GMR and TMR, which is our hard disk drives nowadays working on. And the ferroelectric and multiferroic materials, you have the piezo, para, and especially these material class of materials you are working in the RAM devices. So about top these devices, I'm going to talk about ferroelectric and multiferroic materials, how these materials are important, because I cannot go into the details of all the 6 class of magnetism and the magnetic materials. That will be a huge topic and huge requirement of time. So I will just limit myself. I will downgrade myself towards certain properties, especially the ferroelectric and multiferroic materials. When you say the multi, that means more than 2 states, or you can say the 2 states. So these are materials which have got dielectric, ionic, and crystal type of properties. They have the spontaneous polarization. So, for example, you have lead-based materials, which is being nowadays rejected because of it is toxic properties, health hazardous properties. So we may say barium titanium, which is one of the important aspects of these materials. And one of my PhD students, Dr. Ritesh Kumar, he has worked on many of these materials, and he just put his focus on how we can exclude the lead-based materials. We just remain, barium titanium-based materials, which can be synthesized on and they can be at low temperatures. That was one of the papers he contributed, how low temperature-based barium titanium can be, synthesized, and also without the lead-based, how the lead can be avoided from these materials. So I may show you in the next slides probably about those papers if I have included them. So in case you are doing about the ferroelectrics, so you can see, you can relate yourself as like a paramagnetic materials. They have the random in the A part. There is no polarization here. So the overall the polarization are random. And when you are applying an electric field, almost all, I can say, they just the polarization get aligned in a particular direction, and they have like a remnant polarization. Based on this, we can have a S-type characterization like we have in MH characterization. Here we have PE versus P polarization versus electric field characterization, which is similar kind of a polarization of magnetic polarization, magnetic field, when we apply a magnetic field to some material. So you have here remnant polarization, you have your porosity field again, and all the characteristics determine how a ferroelectric material which can be used for a RAM device should behave. So based on that, it can be said that it is a hysteresis loop which has got double well energy. So it's a two or more than 2 states. Since it's a multiferroic, it can have many states. Among that, I said we are going to talk about barium titanium oxide, which is a material which has got this is a structure of the barium titanate, and it's one of the important materials. Why? Because when you look at the phase transition of this material at high temperature, it is behaving as a cubic material, electric properties. When it's tetragonal, it is at 130 degrees centigrade. At 5 degrees centigrade, it shows something other properties. It is orthorhombic. And at minus 90 degrees centigrade, it is rhombohedral. So you can say there's a phase change in these materials happening, which is quite unique, happening, changing the structure of the material, and the polarization is accordingly changing from 001 plane to 111 plane. So this is at all, you can say that's from the barium titaniate or strontium titaniate doped with niobium and other materials. You have this 28 giga per bit per centimeter square. This is the line width where you can, in less than 20 nanometer, you can see how much the energy, how information can be stored actually. So RAM devices, these are the devices which where you can write electrically, but you are reading magnetically. So earlier in the phases, you remember that we were using that prototype of the CDs, or we were using the floppy disk. They were just readable. Once you exhaust it, you burn it. You just were able to only to read it. You cannot rewrite it. You cannot delete from it. But however, as the advancement of the nanotechnology, as advancement of the material science happened, we could make the changes in these type of materials, and we can now rewrite these. We can just delete the information what was already written. So now the process of writing electrically and reading magnetically has become more sophisticated in that fashion. So as I mentioned, I will present some of the work which I have done in this spot. So we require an S-type of structure to determine whether this material can fit into the BRAM application or not. So in that case, this is the earliest one of the works which was funded by the National Plan of Science and Technology in association with King Abdullah University of Science and Technology. So here we have used the bismuth iron-based titanium oxide, and what we achieved from this, going into very shortly, this is a structure. It was not a single phase based structure. However, we had some limited dielectric constant and conductivity losses here, which were less than 1. So we went for the P loop tracing, and we couldn't find out as the S type of it was just an elliptical loops, and very narrow remnant polarization was. So basically it was not giving us what we were looking. And then what we achieved, that okay, we had a little bit of polarization. This could let me not go into that detail. Rather, we went with the change in doping, and we changed the material. From bismuth, we went to the barium. So we choose here the barium-based materials, replace it with the neodymium. And that helped us in some way to have a better type of a loop structure. And you can see that the loops have gone little bit wider, but again they are not elliptical. They are not the S type, as we were looking to determine the ferroelectric properties of these materials. So what we did, we used the same powder material. We thought that okay, let's not waste this material, and we used this material, and we press it into a pellet and use it as a target material. And with the help of the E-beam, we developed a thin film. After developing the thin film, what we got this better loop enhancement. So loop has increased, and this it has gone from 0.3 to very wide to 140 microcoulomb per centimeter square was the remnant polarization achieved for the voltage of almost 15. So that was a kind of a remarkable thing. So for the application point of view, we got to know that it is better to perform to have the thin films rather than going into this kind of a powder materials, because powder materials are not giving us what we are looking at exactly, from the application point of view. So we just went ahead of this. So since Swift heavy ion is one of the before let me just remind you, the Swift heavy ion, these are the heavy ions which have the energy of 100 MeV to 200 MeV. They are very fast, being used in accelerators, and we have in India one of the biggest nuclear accelerators, or ion accelerators, which is located in IUAC, Inter-University Accelerator Center in New Delhi, India, where I have been working with a couple of legends like Dr. Foran Singh and Mr. Tripathi. So Dr. Tripathi also. So we used SHI. We decided that okay, how we can use these type of materials to enhance their properties is ion beam implantation. So in the ion beam implantation, one has to maneuver. He has to think about how we can use the radiation, because the radiation are going to create the damages. So damages could be, it can have the localized effect, it can have the columnar effect, it can have the multiple defects. So you have to determine what sort of energy range you are going to pick up, what's the stopping energy range, because once the radiation is coming, an ion is impounding on your material, it can either pass through it, or it can just be absorbed, or it can remain inside it, or it can be retracted back, or it will go just close and just it will create some energy just it will pass energy by coming nearer and then it will reflect back. So accordingly, we have to determine the stopping energy ranges. We have two types of stopping energy. We have nuclear energies or electronic energy losses, we can say. So if you have to determine your material, there is a program, software based, we can make the analysis how this could damage our material, or what sort of damage can be helpful. So why the damage? If you look into ion beam technology, that's being used also in Intel Core chips. Before an Intel Core chip is being installed in your computer or the laptops, it is getting through the SHI almost 8 times. So that is kind of you can say the tuning of the properties. So some of the properties can be tuned through it. So here is the radiation damage of materials. Radiation damage is initiated by Frankel peer production. So you can have Coulombic interaction, which is sort of where the defector of clusters, point defectors can be created. Dislocation can happen. From certain quarters of your material, the atom from the atom, the ion electrons can be plucked and it can be transferred to other part. So that way you can have the the different type of properties. It can be designed accordingly. So here you can see that the damage is being controlled in two ways. Either it is the flux, how much flux is being irradiated on your substrate, or it is about the time of exposure, how much time your material is being exposed. That's the second part. And the third part is how for the particular damage, what type of radiation you have chosen. And the fourth part is the energy of your beam, how much you are going to accelerate. It is 100 MeV, it is 150 MeV, 50 MeV, or 200 MeV. What sort of beam you are requiring. So those parts, as I mentioned, this is the 15 UD Pelletron Accelerator Center available in New Delhi, India. And this is the material beams line at the basement of it. And you can see this is the control room. I have worked in long back, and there you can see my face is very different. And this is one of the oldest picture I am using here. So what we choose here from the different ion beams is nickel, 120, silver, oxygen, and lithium. These are the different ion beams, and according, as I mentioned, that you have to calculate the electronic loss. You have to also calculate the nuclear energy loss values, and accordingly you can determine your range. What should be your range of the beam, and where it will come close to your substrate or material, and how the damages are going to happen. So what we did, after concluding our we used the gold irradiated materials, and the stopping energy range you can see, and the projected energy is given in this graph, and 150 mega electron volt with the flux of 3 into 10 to the power 15 was used for 10 minutes with the constant scanning in the 1 centimeter square was chosen as the sample size. So here you can see after the damage, there is a damage. You can see clear cut damage where you can see the columnar defect has happened. This is due to because of the Coulombic interaction is happening, and it's a heating. You can say along this part, the kind of scattering or the energy loss is happening, and that's causing these damages. So after going through these damages, which are visible also, visible through this atomic force, you can say the atomic force microscopy is showing us the clear-cut images of roughness, how the roughness of the material has changed before and after. This is before and this is the after. And what we were looking, whether this could achieve the S-type loop after the irradiation of this. Yes, we were able to have some kind of a S-type polarization after the tuning of this material. That was a remarkable achievement. That yes, we with the tuning of with the usage of the IUCs or beamline facilities, we can have the tuning of the properties. And what we achieved was 36.22 microcoulomb per centimeter square for the 0 concentration, and 109.86 microcoulomb per centimeter for 0.1 doping. That was something very fascinating, and we were looking that is it possible that we can use this type of technology, use this type of synthesis mechanism to do further uh, enhancement in our properties. However, what we did one more kind of thing that was this is it has not been yet communicated. This part it's still under the investigation. And what we did, the bottom of the film was being heated while we were not heating the top one, and we used the top electrodes, and we used this P measurement. What we saw after heating, there is an opposite polarization. There is a leakage current is happening that is pushing the polarization peaks from the origin. You can see from here where it is, the loop is, and where the loop are here. They are moving upwards from as the temperature is increasing from 100 degrees centigrade to 200 centigrade, and this electric polarization, remnant polarization, is also increasing. But that's called a Schottky defect, and it's a leakage current which is happening, and we cannot say this something a great application of that part. It's just opposite polarization happening because of the leakage currents, which I have already summarized, and I don't need to mention this. So this is the conclusion part, that with the introduction of the neodymium, that was a one beneficial part. We used IUC's beam energy technology to enhance our properties. That was one important aspect in this fabrication of the material, and the RAM characterization is still going on. So I may not go into the basics of these multiferroics. As I mentioned earlier, these are multiferroic stores, but you may question that why the introduction is again, because I am going to show you something more related to this part, since we are talking about ferroelectricity, ferromagnetism, ferroelectric properties, multiferroic properties. So these are the various different kind of materials, oxide materials, which can be tuned together, which have these properties, the common properties. They can be pyroelectric, piezoelectric, ferroelectric, ferromagnetic materials, and they have somewhere the conjunction. That conjunction is called actually the multiferroic materials, and that can be visualized through this part. In that part, we had one group of people. This is one of my important collaborator, Majid Niaz. He's from Pakistan, and we started doing this the BFO. We use the same benchmark BFO. Could it possible that we will do the co-doping in the PR doped potassium and cobalt? And what we achieved, we were looking not only this material could be used as a ferroelectric material, or we can design this material for RAM application. We decided that is it possible that this same material can be used as EMI, electromagnetic shielding. Electromagnetic shielding is a very important part, where we can say that our electronic instruments are getting influenced, are getting manipulated by the electromagnetic radiations from other devices. So that radiations are very important to be neglected. So you have your devices, you have your mobiles, computers. They need to be non-interactive. How these materials, these devices can be shielded from the outer influence of the beams or the signals. So there it is, electromagnetic shielding is taking care of. So we were looking, is it possible that we can use this, because this man Niaz has a very good hand in the electromagnetic shielding part. They have the networking analyzer available there. So hello, somebody is saying that my voice is not clear. Is it to all, or it's to some particular person? Can somebody confirm this, that I'm audible clearly? Hello?
You're audible, sir.
Okay. Okay. Some people are having some issues with this, or maybe it is their internet connection. Thank you very much for confirming this. So moving on this, then we, as I said, that we were looking at how we can, use this. So we had two mods here. We have transverse mod. In that transverse mod, what we saw that Q factor absorption was achieved at 1.2 gigahertz, and then again at 2.4 gigahertz was shown with the, you can see it at by the blue dots. So the absorbance was very high. What we did, we had used that different thickness of the material. It is you can say that 0.5 mm, 0.7 mm, and 1 mm. So different materials thickness had shown different absorption properties. So absorbability was achieved at a greater strength, and accordingly, we have proposed, this is a 2D and 3D periodic structure, how these cells can be designed to show that this material can be used for EMI shielding. And as I mentioned, that we are just not looking that is it the perpendicular mod or it's some parallel mod. So what we try to do, we had a different idea that could it be possible that we rotate our material from 0 degree to 20 degree, and we can see how the absorbance is happening. And you can see that with the 0 degree and 20 degree, how the absorbance, it is almost on the same scale, but little bit I can say that the 20 degree which shift in the was better, but although it were coinciding on the same scale, so not much difference, not huge difference. And absorbance was at 2 gigahertz, so we can say that we were crossing the X band region. So this is the again the conclusion of this part, which we already discussed. Then we with another group of people, we had the same barium titanium oxide. Then what we did, we used the piezo magnetic properties, and we collaborated it with the piezoelectric properties. So combination of these and some kind of a composite structure was prepared. And the composite structure, you can see this is done when the BTO for the X composition equal to 1, we have assumed almost a better loop structure with the higher polarization value compared to the 0.0, where we have only this material. That means this is the main material which has been retained there. So that is a kind of a remarkable difference, that it is actually the BTO where from this parallel properties are emerging. So it was quite evident that we can have the parallel loop better in this prospect. However, as we were preparing the composite, we thought that could it be, somewhere the composite can give us the better loop structure, because it's not only the one part of the property we are looking also for the other properties, like how the paramagnetic properties are being utilized. And then when you are talking about the electromagnetic shielding, there are two parts we need to materialize. It is permittivity loss and permeability loss. We have to manifest both the two. So in that case, we were better going. So this is the one part of the properties which I already discussed. This is the second part of the material where I'm going to talk about that how this other oxide materials, such as I discussed, that there are various types of oxides and we have many challenges. And one of the work done by my two students, Dr. Ankush Chauhan, who is right now in Chettinad, and Dr. Ritesh, who has been earlier working in MIT, and he has just left the institute and is working in another institute and he is doing one remarkable work. And these two guys, they prepared this zinc oxide material and they doped this material with the silver, and this was all green synthesis. And in the XPS, you can see the position of the oxygen and zinc was visualized, and everything was going well. And I may not go into the details of these XPS and binding energy of these. So this is what they did, but photocatalytic activity was done by these material, and we saw that Congo red is showing much better, and methyl orange. These two were the materials which were tested with the doping of the zinc silver inside the zinc oxide. So they found that 96% and 38% of the conglomerate and 94% and 35% of the methyl orange were removed using silver based zinc oxide materials as compared to the pristine zinc oxide materials. So we saw that this is one of the important characteristics of these materials. Negative manifestation of this can be visualized by looking at whether these materials could be used as antimicrobial, because zinc oxide is a dynamic material, can be used for various applications, from photocatalysis, from antimicrobial, for anti-cancer, and so many things have been examined by these various scholars and researchers across the world. And this was one of the also important things what was found, because E. coli bacteria is one of the important bacteria which is water-based bacteria, mostly found in the Himachal Pradesh, and it has affected a lot to the health and at one time in the past. So we just look at, is it possible that to see that this bacteria is somewhere being found or controlled we have through this zinc oxide or this doped ones. And you can see the results, and they showed that this, yes, we have the better control when we are using this nanoparticles based on the silver. So we did antifungal tests also. This is the long story short. So another part of this material, in the oxide basis, you can have the graphene oxide. In this graphene oxide, you have various applications. From one important application which I am working currently is we are using cotton-based materials, or we are coating the cotton with the graphene, and we are looking that is it possible to use these materials for smart fabric, as you can say, not the smart fabrics for the sense that we just to put the coffee or it's hydrophobic or hydrophilic. No, we are looking for different part. That is it possible that the same cloth which we are wearing is being used as an electrical material, that we need to connect it to the battery, we need to connect it in a solar panel, we need to connect it in for the devices I am using for the charging and all that. So that smart fabric basic materials we are working, and thankfully I can say that we have achieved the highest conductivity in our cotton based coated materials. We have used different materials, and which can be googled in the or in the Web of Science. You can find that highest conductivity has been achieved by our group in this fashion. So one of the applications, as I mentioned, that since I am discussing about the various applications, various usages and scopes of the oxide, so I am using from ceramic oxide to zinc oxide to graphene based oxides and other oxide based materials. So here you can see also that we use this material for the removal of the dyes in the without the light and with the light with respect to the particular dyes for the photocatalytic application part. And we use the zinc oxide in when we were going through the SARS a long back. We thought that is it possible that we can use it as a biosensor? Is it possible that we will dope the zinc oxide with some aluminum or other materials, and we can have the good biosensing properties? And the same, we had the idea that when the COVID-19 emerged, and that we can develop some kind of a biosensor with the use of these zinc oxide based materials as we had in the SARS time. So what we had, we got this the designing of this material. We prepared the material zinc oxide and doped with the aluminum, and you can see the current and this ratios, and we got the good detection. In fact, we tried and detected dengue type 2 using this DNA of that. It was attached to it, and we had the good properties of these materials, and you can see the conductance of this can be seen here. Unfortunately, I cannot magnify this since this is a limiting version of this Google Meet. If I will try to do it for this slide, let me see, is it working? Because next I cannot move the slides, that's the issue. So you can see the capstans of DNA probe was done at one point. You can see here at 10 to the power minus 12. So the capacitance was shown, the impedance property you can see. Accordingly, you can see when the DNA probing was done, we had this current, which was better. And you can see in the power region also, we have this DNA probing. And what we saw, the resistance has decreased. The conductance has increased as we had this probing using this Dango. And that was one important part of this. So, going back, as I said in the Mori's law, which where we discussed that we need the importance of these materials for the development of RAM. We need the development of the hard disk. We need the development of memory devices. We need to have the devices which can have more energy, more data storage. So, although we have now iPhone with the 1 terabyte storage capacity, we have high performance. Our RAM are better. SATA type of DRDs are available in the market, but yet we know there is a gap. To go for that purpose, what we need to do, as in general, we need to have the nanocrystals of magnetic materials or magnetic oxides, which can be used for the data storage recording. We can use these materials. We have to miniaturize, we have to manipulate, we have to tune their properties using different fabrication techniques. We have to use different materials with different sizes, different doping materials, and we can use these materials accordingly. And these were the different type of our objectives, how we can do miniaturize these electronic devices. We can use their sensors. Can we use them as a ferrofluids, and can we use them as a drug for the labeling of the for the drug agents, diagnostic materials? So they were the different ideas built. Accordingly, what we decided that to develop any kind of a material, what we needed different synthesis of different kind of materials of different sizes and shapes and of the oxide materials. Accordingly, their scalability will determine how these materials can be toxic or non-toxic. They can be of better yield. To improve the quality of the product, what we need high purity, variable crystal size. We have to narrow down the size distribution. We have to look for the crystal structure. We have to look for whether it's a 1-dimensional, 2-dimensional, 3-dimensional. Accordingly, we can determine our properties. This do we need the monovalent or monodispersive, or we need the aggregated or non-aggregated materials? These will sum up our overall idea of looking our future. So in that case, you can see instead of making the transitional components nowadays, what we are doing, this is the if you look into the iPhone 16 Pro or 16 Pro Max or 15 Pro Max, they are using using 15 nanometer the chips. So this is bionic chips they are being used. In fact, now the latest one is going to be the 7 nanometer bionic chip. In that bionic chip, you can see that billions and billions of transistors are being built. And there's another company which is coming up with the latest device, and it's actually an American company which working with the Taiwan company. They have built a new CPU, I can say, or GPU, which has 2 billion transistor chips. So in that case, similar kind of a work we are performing. That is it possible that we can dope our material for spinal ferrites with different types of elements, and we can anchor and we can miniaturize or we can manipulate their magnetic properties. So this is a one part where we use the graphene, cerium doped spinal ferrite with the graphene. So you can see that overall the magnetic properties were not much. So you can see 20 MeV was achieved. In the next part, the same, you can see the cerium doped material which is there, but there is no graphene. So however, you can see the magnetic part, the saturation magnetization has gone above 40 EMU. And in the third part, you can see where we have done the low temperature synthesis of this material, removing certain parts. We have not used the cerium, and what yet we have achieved higher at 300 Kelvin. You can see that magnetic properties are getting much better. The MH loop is getting above almost to 45 EMU. Similarly, you can have the different classification of these materials. Like you have, for example, you have the ferrites. You have the three different types of ferrites, and accordingly, you can divide them into M type, Y, X, Z type ferrites, and then you have for example, EMI shielding, which was the main topic I was going to talk about. So let me use that. We have this hexagonal ferrite basic materials, and these hexagonal ferrite materials are very important in order to develop any kind of EMI shielding. So are antenna basic materials. So what is actually happening in these? I may not go into the details of this. So let's go to the mechanism. It is, we have the three parts here. We have absorption, you have the reflection. This is the material. Here you can see this absorption happening inside the material, and here it is the direct incident one and is the reflected one. And it can be possible that you can have the multiple reflections. So you can use the ferrite materials for the electromagnetic shielding, and in that case you have to design your material with the better permeability loss and permittivity losses, and few results can be seen here, which we have earlier published. And here you can see it is the absorption is for particular doping going upwards, and this is in the gigahertz region. In fact, we have done better than that. This is a long back result which I am showing here. In the recent 2025, we have been able to have the absorption approximately around 70. That has been published in Polyhedron Journal. So this way, these other application of hexagonal ferrites you can determine. So overall, what I will conclude with this my oxide basic materials, that oxides are very interesting materials, and you can manipulate with their sizes, you can manipulate with their shapes, and accordingly you can determine the properties of these materials, especially the ceramic oxide materials. You can use them for the health purpose, you can use them for energy purposes, you can use them for the environmental application, for example, for removal of the hazardous dyes from the wastewater. You can use them for electronic applications, for designing the memories and the chips, and for diagnostic purpose you can determine them as a biosensing devices, and detection of vitamins and proteins. That's also one of the our projects which we have submitted in recently in the Saudi Arabia, how we can use the channel, determine, build some certain channels inside the transition metal junction based devices. I have just removed that slide because I was not sure that should I show that slide right now, because it's an early stage that how we are using that thin film based materials using transition metal junctions, and then building certain beads, and those beads can act as the channels to detect the proteins and vitamins, and it will be just simply a diagnostic purposes, where you can just put the blood sample on the surface of the screen, which will act as a virtual hospital, which will give you all the details that yes, you have this and this and this issues. You need to look the doctor, and it will generate a report, and in fact it will be much helpful to the doctor to analyze the patient and his related issues. So with this, I would like to thank all the participants, listeners, for giving a patient hearing and listening to me, and for allowing me to present some of the little work. I was not sure that I could make it in this particular time. Thank you very much. And if there is some comments, some suggestions, some questions, I'll be ready to hear them.
Thanks for your nice presentation. Participants, if you have any queries, please type your question in the chat box, or you can unmute yourself and you can ask me. Sir, very nice presentation, sir.
Thank you very much. I'm very in-depth thankful to you for giving me this opportunity, and
We are also delighted to have you as in this guest in this forum, sir.
thank you very much. Thank you very much. I look forward that we will have the more events, and I may personally visit the center, and we can discuss
Sure,
some more
welcome, sir.
science.
Participant, if you have any queries, in the chat box they may ask some questions, sir. But as of now, there is no question, sir. We can check the chat box, sir, if possible.
Yeah, let me check the checkbooks and. No, I cannot say it, but I'm thankful to the people for appreciating my talk. Most of the people are, giving their views about my talk. They have somewhere found my talk very interesting. I'm very thankful to all of you for liking my talk. I appreciate that.
So Dr. Sadish Mani is also working in the ferrite, sir.
Okay.
He commanded in this forum. He is also working in the ferrite material.
All the ferrite people are most welcome to collaborate with me.
Sure, sir.
We will have our big one family.
Thanks for your presentation, sir. I think there is no other questions.
Thank you very much. Thank you very much, and see you next time.
Thanks.
I wish you all the best, and thank you very much from the bottom of my heart
Thank you,
for
sir.
giving this opportunity.
Thanks for your spending your time during the passing time with us, sir.
Thank you. My pleasure.
Okay, bye.
Bye.
Participants, the feedback link will share shortly. So please fill the feedback for the national seminar and the international seminar. So those who are filled the feedback, they will get the certificate for this. They will get the certificate for this workshop and seminar. The separate certificate will be provided for this seminars and workshops. So thanks for your participation. So kindly fill the feedback forms.